Welcome back to the last session of the boot camp. We're super excited to have Andrea with 2 lectures on, I think, applications of AMP or AMP and related matters. So this is the first time that I won't be bored because I'm getting a board talk. I'm kidding. I wasn't bored at all. It's been a great boot camp.
Okay, thanks the organizer for putting this together. It was a very nice week. And yeah, as many of you are not anymore used to this, so you'll forgive me if I will not be as polished as pre-pandemic and not used to this technology anymore. So, okay, so I'll talk about 2 things, 2 problems. The first half is an estimation problem. It's actually a continuation of what Cindy has been talking about in our lectures. It's low rank metric estimation. You have a vector u in Rn. Okay, and we think of the norm of u as scaling as square root of n, and we observe u transpose divided by n plus noise, and the noise will be Gaussian with variance of the entries of order 1 over n. And the problem is, given the matrix A, this is an n by n symmetric matrix, I want to estimate the vector u, and I want to do it efficiently. And the second question will be an optimization question. I have the same Gaussian matrix. Now I want to optimize this objective sigma w sigma, and the point is that I will have a non-convex constraint on sigma, and the constraint that I'll focus on is this one, but okay, presumably the ideas are somewhat more general. Okay, and the kind of algorithms that I look at are what we call the GFOMs, for generalized first order methods. And okay, so these are algorithms that proceed by 2 types of moves. Okay, first of all, I initialize the algorithm with the vector x naught. So whenever there's a vector, I put the time index superscript in Rn. And then iteratively, this is iterative algorithm, at time t, I have stored t vectors, x0 of t plus 1, xt. So these are vectors all in Rn. And I can do one of 2 things. I can do either one of 2 things. 2a, let's say, is just apply a nonlinear function that acts coordinate-wise. Okay, so here the convention, as in Cindy's lecture, was that this is a function from rt plus 1 to r. And when I apply it to t plus 1 vectors, what I mean is that I put this vector one next to the other, and then I apply row by row. Okay, so this is the matrix x0, xt. This is a t plus n by t plus 1 matrix. And I overload the notation. By this I mean that I apply the function and row-wise to this matrix n by t plus 1. So I can do this thing, and the other operation that I can do is I can multiply by a. Okay. So these are the 2 kind of operations that I want to do. And perhaps at the end of the day, I will output an estimate at some time capital T. I output an estimate that is some function of all my iterates, where again, G is some that applies with the same convention. Okay, so perhaps I should start changing things a little bit. I'll call this actually capital F. So does the definition make sense? So this is a definition that I like because it includes a bunch of algorithms that we know. For instance, if I do gradient descent with respect to an objective of the form xax plus some phi of x, where phi is separable, then it fits into this business. If you do some nonlinear power iteration, it fits into this business. Some low order, low degree polynomial fit into this in this framework, but not all of them. So for those of you that are into low degree polynomials, I'll say just one word: low degree, because correspond to low degree polynomials with let's say indexed by trees. Trees in the complete graph. I can, if you want, I can describe this more, but it's not the focus. And okay, this framework is not completely general in the sense that this nonlinear function applies row by row. I think it's possible in principle to generalize to some non-separable functions, but this has not been done. Non-separable. So let's put question mark. Let me put question mark. Okay, so this is the algorithm that I want to analyze. And let me start from a first remark. Remark number one. Without loss of generality, I can eliminate this alternative, and I can decide, can always do xt plus 1 equal ft of x0 xt. I should add that in what I'll do typically, the f are nice functions. Let's say that they are Lipschitz. Although even this is not really important. Oh, here, of course, I did a mistake because I didn't write anything new. A times f of xt. So I can decide that at each iteration, I apply this nonlinear function and I multiply by a. And there is no loss in generality in this because I can always postpone doing this stuff, right? Because anyway, those vectors are stored, so I'm fine. Okay, so claim number two, remark number two, is that if you give me a sequence of function, let's say f hat t, that are always from, let's say, rt plus 1 to r. Now you tell me, you have to work with this kind of iteration. At each iteration, you don't have a machine that computes this and multiplies by matrix A. I have a machine that, for some reason, computes the function that you want, multiplies by A. You have an oracle that does this, but then subtract this error. This is a known function, okay? Or subtract this shift, okay? I claim this. I claim that if you give me, if you're constrained in this way, I can still simulate any algorithm of the previous type. Namely, yeah, if I want to simulate.
So there is both f hat, like there is a
right. So yeah, so this. So suppose that I want to implement this, okay. And you build the machine that the oracle that says compute this, and says, okay, I can give you only an oracle that each time computes the nonlinear function that you want, multiplies by the n by n matrix, but then look, it will subtract this shift. I claim that I don't care about this shift because at the next iteration I can modify my next nonlinear function by adding the shift back. Does that?
You get to choose little ft, but not that path. That path is known to you, but it's not under your control.
It's not under my control, but I can still compensate for it by adding it back at the next iteration. Okay, let's see in a moment. Why am I making this remark? Yeah. Well, I can give you a nasty answer. That is because I'm doing the lectures. No, but the reality is that this is a very good answer because it will be answered by question, because it will be answered by the next theorem. So theorem. So this is the AMP state evolution theorem that Cindy gave several examples of, and I will give one example that is a slightly generalization. And okay, so assume that you have you have some convergence on the spike of your matrix. So you have the spike here, and then you have the initialization somewhere, right? You have the initialization, right? So I assume that the joint empirical distributions of the entries of these two converges. To some p u x0. Okay. Okay, let me call it z0. From now on, I switch to z for no special reason. And I claim that for any sequence of functions ft, Lipschitz, there exists a sequence of function f at t such that the following is true, setting this iteration, so zt plus 1 equal a ft z0 zt minus f at t. They exist and they are Lipschitz and they are completely explicit, but for the moment it's not important to write them down. Looking at this iteration that I wrote there, then the following happens. We have, okay, let me write a small notation. Nothing, I don't know exactly. In my note it's changed, so I don't. Thank you. So let me write it as, and then. So, okay, here I'm gonna, so this is a very synthetic notation to mean that I'll use in the following a little bit, to mean the following, that if I look at the empirical distribution of the entries of this vector, delta ui, z0i, zti, this converges, for instance, distribution weakly to what? To the law of u z0 zt. Okay, so this is the type of theorems that Cindy presented in the last lecture. You look at t iterates of this algorithm plus also the spike. You look at the joint distribution, so you can put all of these in an n by t plus 2 matrix. And I think of this as n data points in dimension r to the t plus 2. So each this is a row of this matrix. I look at the empirical distribution of all of these objects. So this is the probability distribution that puts mass 1 over n on each of these points. I claim that for large n, at any fixed t, this converges to a well-defined limit that is the joint distribution of this t plus 2 random variable. These are capitals, so they are random variables. And these t plus 2 random variables have the following structure. Well, u, z0, we already know, these are data. And then z1, zt are very nice because they are a vector, a deterministic vector times u. Okay, u is the random variable, plus Gaussian noise. Okay. And so if I call this G is normal 0 sigma. Okay, and so all the distribution is determined by this vector and this matrix, and these obey this. So this is independent of u z0. Okay, and I can determine, I can give you equations that determine this vector and this matrix, and the equations are like this. The equation for mu are, perhaps it's clearer if I wrote there. The equation for mu is mu t plus 1 equal expectation of u ft of z0 zt, and sigma t plus 1 s plus 1 equal expectation of ft of z0 zt fs z0 zs. Okay, so this theorem is saying, and again is an example of what she described. If you look at the row of this, the distribution of the row of this is completely asymptotically determined by the sequence of number mu that give the mean and the correlation with u, and by matrix sigma, and this can be determined recursively. So perhaps at this point I should stop a minute and ask if there is any question. Yeah.
So maybe I'm missing something, that there's only partial information about your goal is not going to be recovering u, but only like the bag of the values of the entries of u.
No, my goal is recovering u, and this tells me a way to recover. For any given algorithm, I can use, for instance, zt. So zt is a vector. So what this tells me formally, this theorem, that the entry of zt, the joint distribution of the entry of zt and u, these are ordered. So 1 over n. So let me make it even more complete. This tells you that 1 over n sum over I 1 to n of any function psi of zti ui, this converges to the expectation of psi of this random variable zt and the random variable u. Okay, so in particular, you can take any algorithm of this form that I wrote here. Okay, and you get a correlation between, you can compute, for instance, the correlation between this and u. And you can compute the exact limit of it.
Based on yesterday's discussion, you anticipate that u is an increasing sequence, and it's a meaningful sequence when the model is above the information theoretic region, for example, because you could this applies whether it's above or below the information theoretic region, right?
Yeah, this is a completely general fact.
And if it's below, then you get u's which are right.
So the question is, at least, so the question within this type of algorithms and within, by extension, by this reduction within any general first order method, the question is, how should I construct the sequence of functions ft? If I construct, so the question is, design optimally so the optimal define of a generalized first order method just reduces to the optimal design of functions ft as to maximize this correlation when the random variables are generated in this way. This reduces the optimal. And of course, I have in mind that always at the end of the day, I can take all of my values. So here I brought an estimator that is just take the last iterates, but I can compute any function g of zi 0, zit, and ui, and this will be This one will be my estimate of what you have. Okay, so at time t, I can accumulate my t iterates, apply row-wise any function. And so my real goal is optimally designing both this function ft and this final post-processing function g. Does that make sense? So in the last, yesterday, Cindy showed that, just to make contact with what she was doing, she was looking at the case in which this function depends only on the last iterate, and she showed you how to construct the optimal function in that case. Now my goal is a little bit more ambitious. I want to go over all functions with memory, because in this way I will catch all of this generalized first order method. And my claim is that actually you end back to this exactly the same sequence of function that Cindy derived.
So it's a principle like you could imagine a first order method, generalized first order method that doesn't use the right shifts, but you say that this would not be, that it wouldn't be a good method.
That doesn't use the right?
That doesn't do these kind of shifts, right? So this is only state evolution when you're using the right kind of shift.
Right. But what I'm saying is that any other method that doesn't do this right shift, I can just simulate it by first running. So let's call the algorithm with the right shift the AMP algorithms. I claim that any first order method, any GFOM, I can simulate it by running an AMP algorithm and then doing a post-processing. And this is just a union of these two
so now this is
remarks. Now, if you are nitpicking, you will notice that really this remark is a little bit weaker than this, because here what I'm telling is you first tell me F and then LF, while here I told you there exists F, so in principle this F and F could be related in some nasty way, etc. But in reality they are not. This is carried through, for instance, in the paper of with Yu Chen and with Michael that is published, and that reduction is explained in detail there. Other questions? So perhaps an interesting remark is that this iteration, so there are two iterations, one for the mean and one for the variance of this, the covariance structure of this Z. Notice that the one for the covariance structure has a very nice interpretation. It tells me that basically there is an isometry, the covariance of the F is the same as the covariance, this is the covariance of the G's, right? Sigma is the covariance of the G. So this tells me that, okay, the F's, of course, they are not Gaussian in general. The G's are Gaussian, but the two are isometric. They have the same scalar products in F2. Okay, so it's a, it might be useful for you to make sense of this iteration. It's just saying that the G are Gaussian variables that have the same covariance structures as the F. And also, if you look at it, this kind of theorem also tells me that, for instance, between this Z and this U, there is, this variable and these variables, there is a correspondence such that you can think of this basically as the infinite dimensional version of these iterates. And this is what I'll do. Okay, so now I want so I claim that I can reduce always to this thing plus the post-processing. Now I want to design those functions. And for that, I'll use another claim. Perhaps this is claim 3. And it will be the following. Assume that by this I mean Z0. I want to stop writing Z0, Z1, Z2, ZT. I write Z less or equal than T. So now we know that in the limit, this is given by sigma. Assume that it concentrates, this is not, in view of the theorem, is not really an assumption, but I want to write this claim more generally. Concentrates around sigma TS. Okay. Again, this assumption in reality is implied by the theorem, but I want to write it as a standalone assumption. And also that lambda mean of sigma, so lambda is a nice condition number. In particular, this is bounded away from 0. Yeah, so this is deterministic. So this is a strictly positive constant. So this matrix is invertible, then can reduce A and P. Can reduce to the case in which 1 over n, let's see, 1 over n is any matrix MST plus small of 1, where M is any positive for any M that is strictly positive definite. Yeah. Here, I told you this way. I told you come up with some F's and then you compute sigma. I claim that I can go the other way around. I can determine the covariance first. I can decide any covariance. And then I can come up functions with determine that covariance. And modulo changing the post-processing, I will not lose anything in accuracy. I can reconstruct all the algorithm that I had before. And the trick is very simple because
O1 and what's the substitute?
O in probability. So something that goes to 0. Okay, and the trick is very simple. It's simply that since this is invertible, suppose that you come up with a sequence of F that don't match the covariance that you want. You can always whiten them. You can always multiply by sigma inverse at one iteration, sigma minus 1/2, and then multiply by sigma 1/2 at the next iteration. Okay. So I claim that if you give me this sequence, then basically, so the claim is that if you have an algorithm that for any algorithm I can achieve the same performance by an algorithm that has a pre-assigned sequence of scalar products. Does that make sense? Okay, so if that is true, then of course, a convenient choice is that I will choose this to be the identity.
Wait, sorry, maybe I'm missing some checking. The multiplication by sigma minus F, how does this play with the assumption that F is separable?
Well, it's okay, right? Because if I have F
N by N matrix, T by T matrix.
Right, so F by T, then I multiply by sigma, let me call it sigma. So this is now this is a matrix that is N by T plus 1, or let me call it 1, N by T.
Yeah.
This is it. And then
Okay.
I multiply by this, and if I want to achieve, so this is this multiplication by sigma 1/2 is row by row.
Yeah.
And so I can undo it in the next iteration. Okay. So I can operate with F that are orthogonal, basically, and this is convenient because that will mean that this noise vector is independent Gaussians. Okay, so under that constraint, my optimization, my algorithm design question becomes the following. my algorithm design question comes simply, say that I want, okay, let's fix our ideas. And so far I didn't talk about any loss function that I want to optimize. Let's say that we want to estimate U as to maximize the scalar product, well, perhaps divided by the norm of. Okay. So let's say that this is our objective that I want to optimize. Well, what our theory tells us is that for large n, this objective will converge to this quantity, will be the expectation of the random variable U times G of Z divided by, and Z here is a vector. It's the vector until the final time divided by so I want to maximize this subject to what? Two things basically. The first constraint is that ft of z, f of z is equal to delta Ts. This is the Dirac delta and the Kronecker delta. And the means satisfy the iteration that I wrote before. And that Z is, of course, defined as and these are simple. So this is now the algorithm design problem. I want to choose a sequence of function f and a function g to optimize this thing. Okay, now the function g is very easy to see. To compute what it is proportional to the conditional expectation given all the rest. But okay, let me not compute it in this set, but let me just say that q is an increasing function. You see, observing this thing is equivalent to, now there is an optimal linear combination of this t observation, t independent observation, and the corresponding SNR is I claim I want to let's look at the problem of optimizing this over G. I'm observing, I want to estimate a random variable U, and I'm observing T independent observation that are coefficients plus U times noise. Well, there is an optimal linear combination of these. The optimal linear combination is a weighted sum. It's mu I Zi. And the SNR of this optimal linear combination is exactly the normal. Okay. So because of this, this is T, of course. Because of this, what I want really to optimize, so I can forget about this objective. I really want to do, I want to optimize the norm of the vector mu, where mu is determined by the f's to this recursion. Okay, let me write it in an even more compact way. Make the solution of this problem more obvious. I can define a random variable here that I call fs. This is the random variable that is simply obtained by applying the function f to z1, fs to z1 to zs. So what I want to do, I want to maximize sum over s less than capital T of mu s squared, subject to Okay. That is. Right, just. And so what I really want to find is a sequence. So I have a sequence of independent random variables. This, you can think of this as generating a filtration. Fs is sigma of z less than s. So I have a sequence of independent random variable, and I want to construct random variable ft, where ft is measurable on sigma algebra ft that maximizes this news.
Andrea, see?
Yeah.
I mean, the optimization problem is just the 3 lines that you wrote at the top, right?
Yeah, the optimization problem, and this defines the muse, right? This defines the z's in terms of the muse. So the optimization problem, if you want, is in terms of this random variable f. Now, in passing from this to this, I'm hiding something under the carpet, is that for my algorithm to work, this object have to be, for instance, continuous. I cannot take them wild, measurable functions, while here I'm hiding that constraint. But okay, I can play this game as long as at the end of the day you check that the optimizer is really given by some nice continuous function. Does this make sense?
The point is that after all of these series of reductions, that the best generalized linear method without any of these constraints is no better than the best thing that you can get out of this.
Right. And actually, I can write this in a geometric way. Now, this is just a scalar product. So let me write it as a scalar product. It's just a scalar product. Okay. So if you write it in this way, it's obvious. It's obvious what? It's obvious, there is an obvious upper bound here, right? First of all, okay, let me first write like this. And then let me denote ut e of u given ft. Okay, so this is the expectation of u given the first random variable. And here I can replace this by ut, right? This is the first. You can replace, well, if I have u, let me write it like this, z1 and take first conditional expectation of u. Since ft is measurable with respect to the first t variable, I can take first the conditional expectation given the first t variable, and then the expectation overall. Okay, so I can replace this by t. Okay. And then I'll write this as an L2 scalar product. Okay, and now there is a clear upper bound of ut plus 1. I have a sequence of orthogonal vectors, and I'm trying to optimize this product, the orthonormal vector, and try to optimize the last one times ut. The best that I can do is point in the direction of ut when I subtract from ut the projection onto the first t minus 1. And so I claim that mu t plus 1 is less or equal than what? Then the norm of ut square minus the sum over s less than t fs ut square root. And here, okay, what is this norm? This norm, is just a nice way, this can become, okay, L2 notation is, I think, very useful when you get used to it, but very confusing. This is just this. This is just this, and this is just. Is anybody following?
So is the dot product expectation of FSUT, would that be the same as expectation of FSU? So that would be just mu s?
Yeah, okay, excellent. So not only you're following me, but you're going ahead of me. This I can replace by E of F S US. Because US is the conditional expectation of UT given the first S steps. Okay, so what did we obtain? We obtained the following beautiful inequality, that mu t plus 1 is less or equal than, let's say, square ut non square minus sum over s1 to t mu s square. And this immediately tells me that for any t, the sum over s1 to t plus 1 perhaps mu s square is less or equal than ut. Okay. And at this point, we are basically done because what does this tell us? I mean, so if I find an algorithm that achieves, so this is exactly the quantity that I want to optimize. So the quantity that I want to optimize is the first sum of the first t. If I find an algorithm that achieved all of these bounds, then I'm done. And the algorithm is clear because the only thing that you need to do is saturate each of these, Cauchy-Schwarz inequality. So the algorithm is just take the iteration to be basically, okay, in this notation to be ft. Ft needs to be the conditional expectation of u given ft minus the conditional expectation of u given ft minus 1. And if you now track what this means, this is exactly the algorithm that Cindy described yesterday. This is simply a function of the last iterates of the last ZT. What function it is? Well, it's a conditional expectation of the distribution of U in Gaussian noise. So in the end, we find that the optimal algorithm is simply obtained by taking the optimal algorithm is simply obtaining by taking ft of z0. Zt now one has to pay a little bit of attention because zc0 at a certain point I've hidden things. Z0 doesn't have to have this Gaussian behavior, so you have to treat it separate from all the rest. But so otherwise, you can take this to be the expectation of u given z0 equals z0 and mu tu plus g, where g is standard normal equals zt. Okay, this is not really important, is the initialization, but basically the optimal thing to do is at each iteration you look at just the last iteration, you treat zt as the signal, the right signal plus noise, and then you do the optimal Bayesian denoising procedure. So this gives the optimal error, estimation error, that you can achieve by any GFOM.
There are a bunch of reductions that you've done. So this is not the algorithm that you would use. Like the optimal algorithm can be analyzed using this.
The optimal algorithm is this one. Is exactly this one. The bunch of reduction shows that any other algorithm can be seen. So what? Yeah, let me summarize. We showed that any GFOM will have the same error as one algorithm of this form, plus some very simple post-processing. And the very simple post-processing is form this T+1 by n matrix and do some nonlinear operation row by row. This, by the way, is a completely non-asymptotic, it's a completely deterministic claim that doesn't have anything to do with probability. Hence, what we did is that, okay, so now all that we have to do is look among all algorithms to this algorithm and potentially some post-processing. Since we have this theorem, analyze the loss of any of these algorithms amounts just to solve this optimization problem for iteration in one dimension. For denoising, it's some kind of iterative denoising problem in one dimension. There is standard denoising where you have a random variable and you observe the random variable plus noise. Here, it's a bit more difficult because it's iterative. So I have to solve this one. How do I solve this one? Well, I derived an upper bound, and then I claimed, I didn't do the full calculation, but I claimed that this upper bound is achieved by the algorithm that. And the way I derived to this upper bound is, okay, you can work with this cumbersome notation, but I think this is a bit more insightful. I thought of this iteration as a geometric set of constraints about the iterates. This set of constraints is imposed by my choice to constrain this to be orthogonal. And this is just the dynamics of this algorithm. And once you have this upper bound that now I raised, this upper bound that is just basically Pythagoras theorem and Cauchy-Schwarz. And then I claim again that the only way to achieve this upper bound is that at each step, that in this inequality you saturate Cauchy-Schwarz, and Cauchy-Schwarz is saturated by taking these conditional expectations. Okay, so the
choice of loss function is not special, right?
Sorry?
The choice of the loss function
Yeah.
is special, right? Is it like you get to predict if you have a different choice, but
Right.
it's still in the input.
Right. So here I could have chosen another loss function. So I did this for concreteness, but let's say that I choose another, whatever, as some loss function. Right? Say that I choose E of L of G of Z and U. For instance, I can take L of XY equal absolute value of X minus Y. Or absolute value of X minus Y maximum with 1. So the loss function that I want to optimize, let's say that is the following. I want to minimize this loss function. So this is an interesting universality kind of phenomenon. So I want to minimize this loss function. I described the maximum, but I want to minimize this, okay? Well, so this final process, post-processing step is what? Again, there is an optimal summary of this. This is really a sufficient statistic, so it's independent of the loss, and the optimal summary of this is this one. Right? I can always assume that if I have this vector of observation, I combine them in this way. This combination is some coefficient mu sum. Let's call this mu sum square. Mu bar square, u plus mu bar times g plus mu bar times g. Yeah, it's correct.
The loss will change the post-processing, but it will not change the iterates.
Yeah. So you without loss of generality you do this, and then here what you have to choose, of course, is the function g that minimizes this loss in a problem of estimating of a one-dimensional random variable. This is a small, theoretical statistical exercise to do. But of course, this thing is, you can view it as a function of this mu bar is always an increasing, if it's a loss, it's always a decreasing function, it's always a monotone function of mu bar, just by stochastic domination. So it's always important, what your objective will always be to maximize mu bar. So as Boaz said, all that you have to do if you change the losses, change the final post-processing, but all the iterates remain the same. Other questions? Now, there is an obvious weakness to all of these analysis, that this is limited to a constant number of iterations, possibly to some slowly diverging function of n. Actually, seen as a result going to some slowly diverging function of n, but there is always the mystery of what happens when you go at a very large number of iterations. But as long as we are content with this kind of within this class of algorithm fixes the problem. Here I did the simulation for this low rank matrix estimation problem, but in the paper with Michael, we do it more generally, except that the proof there is more complicated, and now we have this simpler argument that can be taught in.
So the issue is the speed of convergence and state evolution?
Yeah, so the issue is really, proving this kind of result. Now, this kind of result, we know that will not be generally true beyond log n iterations. I can give you examples in which, for instance, if I do this thing and initialize with a random vector, instead with something slightly correlated with the truth, if I initialize with a completely random vector, this will escape this unstable fixed point after log n iterations. And this at the moment, there is no rigorous analysis. And so that is a little bit of a case-by-case analysis. There is probably a simpler thing that is there to be done, that is look at simpler cases in which you reach a stable fixed point and you want to prove that you stay there. Actually, there is some special cases have been done like that in which you keep iterating. Okay, so I guess that's a good time to pause, and then in the next hour I'll talk about optimization, I guess. And that's all.
Completely break. Other questions for Andrea? Okay, we'll come back at 10 past 3. 17. 10 past 3.